Engineering 305, Chapter 1, Problem 27, Problem Statement. A force of 20 pounds is required to pull the stopper DE in Figure 127. Determine all the forces acting on member BCD. There's your problem statement. Here is some of our problem geometry. A little more. Oh, you can't see that. Let me change the scene on you. There you go. There's some more problem. There's some more geometry for you. So, what's given about the problem? Well, we've got geometry. We got a lot of information there. We've got a 20-pound force. Anything else we want to pull out of that? Not yet. Not yet. All right. This is like the previous problem. Can't solve the whole thing at once. We got to solve it in sections. So we're going to start with just this first link. I was like that. I pull up on here, and that's what I know. And that is a 20-pound force. Except right away, I'm going to make the assumption that the problem is symmetric. Assume that the problem is symmetric. If I assume the problem is symmetric, now I can split the problem. And so this is only a 10-pound force, and that makes this a 10-pound force. Well, and I say, why do I know that? Well, because some of the forces, and I'm going to put a coordinate system here, x and y. Some of the forces in the y are equal to 0. So whatever I pull up, I got to be pulling down on the other side. It's also a two-forced member, so I know that the actual forces are running along this line. So if I have that force acting up, and then that means this force has got to be acting out. It's a 45-degree angle. I got that from the geometry. I can copy that over here. I could put this is 1 inch, and that this distance here is 1 inch. That would make it a 45-degree angle. And if it's a 45-degree angle and then that's 10 and it's on a 45, then this has got to be 10 pounds. And you should probably from trig classes know that this tension in that member is equal to 10 times the square root of 2 pounds. About 14, right? About 14 pounds, the tension in that member. Now I can go on to the second part, this BCD part, and I'm going to draw that free body diagram quickly because I'm probably going to draw this 3 times. I've got a tension force here equal to 10 times the square root of 2 pounds, and I've got forces here, and I've got forces at that point. This is C, and this is D, and so those are going to have, and I'm just going to quickly draw them in random. Did I think about the directions much? No. This is going to be the force at D in the X direction. This is going to be force at D in the Y direction. This is going to be force at C in the X direction, and force at C in the Y direction. Why didn't I think about those a lot? Oh, that's point A. Because the signs work themselves out. I'll be fine. I'll be fine. And the other thing is by just, there you go. A statics and dynamics problem, if we're going to solve this single body, how many equations do we have? We've got 3 equations. And I have 4 unknowns. And that is a sticking point for a lot of mathematics. What's my next step? How do I get past that? Well, what else do we know about the situation? That's always what it boils down to. I've got to write one more equation. I've got to write one more equation. Here's my other equation. That is F C E, right? And that point F is symmetric. So I've got that force acting up. And then I could put these on any way I want. These forces at C and the forces at E. But what do I know about the forces? Well, the force at C and the force at C, these have to be equal and opposite. One's the reaction forces. So this is going to have to be like this, and that's going to have to be like that. This force at D, I would expect, because it's symmetric, they're going to go the opposite way. This is going to go outward, and but this would still go upward. Do you see a problem with my picture? This force at C in the y direction is equal and opposite, but that doesn't work. This isn't going to create a symmetric situation if I've got that down. The only way that can work is if that vertical reaction force at C is equal to 0. That's the only way that this is going to work. Now, with that new information, I want to redraw my free body diagrams one more time. I took some time and I got this drawn ahead of time. I can't show it to you. It's just I can go over here and grab this and grow that there for you. The distance from, I redrew this because I'm going to do, it's easier than figuring out angles. To me, it is. These are nice orthogonal. So now my sum of the moments equation about D is going to look like I've got this term, which that's going to cause it to rotate. So it's going to be a plus, sorry, it's a minus 10. It's rotating y to x. Sorry, got that wrong. A minus 10. And then I need to know that distance. Well, if I go back to this picture, it's from D to the center line is 1.5 inches, and then I have to go that one more inch to there. So that's 2.5 inches. And then I'm going to go, I've got to add, that was this term. I got to add this term. That's going to cause it also to be negative. So it's a minus 10. And now that distance is 4, and that's from B down to the bottom, that's 2 inches plus 2 inches. Okay, so that's 4 inches. And then I have this force at C, which I've been drawing, and I just finished up drawing it. It was pointed that direction. That's my force at C in the x direction. That's also going to cause a minus rotation, force at C in the x direction, and that's 2 inches away. I just give you that there. Oh, I'm starting to cover up my formula. Sorry. Oh man, moving the wrong image. There we go. There you go. You don't need all that mechanics of television. You didn't need all that. Minus force of C in it 2 direct, and then that's all equal to 0. And I can add this all quickly together. This is going to be a minus 10 times 6.5. So that's 65 divided by 2 is equal to F sub C in the x direction is equal to 32.5 pounds. And that's, sorry, I dropped a negative there. That's going to be, it's not in this direction. It's actually the way the book is going to do it is minus, or it's going to say plus. It's going to point that way is the way that's pointing. And really it should be, if it's pushing that way, if I show the arrow that way, it should be a positive. It gets confusing, but it's to the left. All right. Now, if I have that, then I can quickly go back and solve for these forces, which, let's see, I drew F, D in the X, and I drew FD in the Y. FD in the Y is just the 10 pounds. That's the only, so that one's easy. And I'm going to say that's up. And then FD in the X, I've got summation of forces in the X direction is equal to 0, is equal to all three of them in the same direction. But I have a 10 and I have a minus 32.5. And so, and then I've got a plus FD in the X. It's equal to 0. FD in the X is equal to, leave that, that's going to be a minus 22.5. It goes over, so it's 22.5 in the direction shown, because that's going back. So 10 and 22, 10 and 32, and did it twice. 10 here and 22.5 here, and that's then the opposite going back that way. So if I want the force acting at D, then I can use a little bit of trigonometry and figure that out, and that's going to yield the answer that the force at D is equal to 24.6 pounds, and we could just draw that triangle. It's 22.5 and it's 10, and that's my vector, and we can go back and calculate what theta is. All right? Very good. Very good. There's problem 127. Except for that little problem that the force at FD is down. And then this triangle, actually that triangle has to look like that. I just caught that if I had written out the equation, I skipped a step. If I had written out the equation, it would have been obvious. The force on the cork is up, the force on the tong is down. That's my angle, theta, which is 22.5 and 10, and this is incorrect. There you go. Now you can have a good day.